Welcome to our fourth lecture. Today is the 5th of November, so happy Guy Fawkes night to you. This week we're going to be talking about vectors, the dot product of two vectors, and the cross product of two vectors. First, vectors. For some quantities, for example, mass, time, distance, etc., we only need a number. But for some quantities, for example, velocity or force, we need a number and a direction. For these, we use vectors. A vector is an object which has a size or a length, and it has a direction. We can think of vectors as arrows. The length of the arrow tells us how big the vector is, the size of the vector, and the direction that the arrow points in tells us the direction of the vector. If we have a vector which starts at A and finishes at B, we can call this the vector AB. This has initial point A and terminal point B. The length of the vector we typically write as two vertical lines, AB, two vertical lines. You might see some books using one single line, but the standard is to use two vertical lines. We say that two vectors are equal if they have the same length and they have the same direction. The initial points and the terminal points don't matter. All that matters are the lengths and the direction. So in this picture, we can say that the vector AB is the same as the vector CD, is the same as the vector EF, is the same as the vector OP, because these four vectors all point in the same direction and they all have the same length. Now note that AB is not the same as the vector GH because the lengths are different, and AB is not the same as the vector IJ because the directions are different. If we use a computer, then usually we use bold font for vectors, bold U, bold V, bold W, etc. It's quite difficult to use bold when we use a pen or a pencil, so the standard is that when we use a pen, we use underlined letters for vectors. So if you see me type AU plus BV, or if you see me write AU plus BV, then you will understand that A and B are numbers. These are not bold, not underlined. U and V are vectors. We're going to be talking about vectors in both R2 and in R3. In R2, first of all, if a vector V has initial point z0, and terminal point v1, v2, then the component form of V is open bracket v1, comma v2, close bracket. We can do the same thing in R3. If we're in three-dimensional space, if we have a vector with initial point 0, 0, 0, and terminal point v1, v2, v3, then the component form of V is v1, v2, v3. Here is a picture of a vector. This vector has initial point P and terminal point Q. So we could call this the vector PQ, or if we wanted to, we can call this the vector V. The component form of this vector is v1, v2, v3. We can calculate this by doing terminal point minus initial point. We can do x2 minus x1, comma, y2 minus y1, comma, z2 minus z1. If we're in R2, then the norm, or the length of the vector v, is given with this formula. Two vertical lines, v, two vertical lines, And then just using Pythagoras, the square root of v1 squared plus v2 squared. And we can do the same thing in R3, but we have 3 components instead of only 2. The norm of v is the square root of v1 squared plus v2 squared plus v3 squared. And if it's the vector from the previous picture, that's the same as the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. The zero vectors, that's bold 0 or underlined 0. Two-dimensional space, that means the vector 0, 0. In three-dimensional space, it means the vector 0, 0, 0. You can see from these formulae that if we put the numbers 0, 0 or 0, 0, 0, we find that they have norm equal to 0. Zero vector has norm or length 0. If a vector is not the zero vector, then the norm of v is strictly positive because the square root of a number is always positive. Now, just to be careful here, there's 2 different zeros here. Bold 0 is a vector. This is the 0 vector. But this ordinary 0 just here is the number 0. Let's do an example. Find the component form and the norm of the vector which has initial point P and terminal point Q. We're just going to do Q minus P. Terminal point minus initial point. So we do minus 5, 2, 2, minus 3, 4, 1. And we look at each of these numbers, each of these components separately. First of all, minus 5 minus 3, that's the same as minus 5 plus 3, it's minus 2. Let's look at the second numbers. 2 minus 4 is minus 2. And the third numbers, 2 minus 1 is 1. So the answer to the first part is minus 2, 1. And then the question also asks us to find the norm of this vector. So we can calculate that the norm of v is the square root of minus 2 squared plus minus 2 squared plus 1 squared. That's the square root of 9 or 3. Here's an example from the Thomas's Calculus textbook. A small cart is being pulled along a smooth horizontal floor at, let's say, 20 newtons force, let's say. Making a 45-degree angle to the floor. What is the effective force moving the cart forward? We can answer this using vectors. The effective force is going to be the norm of F, typically 2 lines here, norm of F, multiplied by cos 45 degrees because the angle is 45 degrees. And when we calculate this, we get 14.14 newtons. Moving on. Let's talk about vector algebra. First of all, addition. We can think about adding 2 vectors in 2 different ways. First of all, we can think about putting the vectors nose to tail. In other words, drawing the vectors so that the terminal point of u is the same as the initial point of v. And then the vector u plus v is the vector which has the same initial point as u and the same terminal point as v. Or we can think of it as a different way. We can think that we could draw the vectors u and v as arrows with the same initial point. We could draw the parallelogram, which these vectors give us, and then u plus v is the diagonal of the parallelogram. If we have a vector, we can multiply it by a number. For example, if the red vector is u, then the orange vector is 2u. These two vectors point in the same direction, but 2u has twice the length of u. Here are the vectors 0.5u and 1.5u. Again, they point in the same direction as u, but their lengths are multiples of the length of u. And this is the vector minus 2u. The length of minus 2u is the same as the length of 2u, but minus 2u points in the opposite direction from 2u. We can think of subtraction as in two different ways. In this picture, I've shown v plus u minus v is equal to u, using the same ideas that we had from adding vectors together. So if we wanted to do u minus v, we could draw them as arrows with the same initial point, and then we could draw the green arrow, which has initial point at the terminal point of v and terminal point at the terminal point of u. Or we could draw a triangle like this. We could draw the vector u and the vector minus v. And then we can do u plus minus v. That's the same as doing u minus v. Now, let's suppose we have two vectors, u and v, and a number k. I just repeat myself. U is a vector because it's in bold. V is in bold, so we know it's a vector. K is not in bold, so k must be a number. We can add these two vectors together by adding their component forms together. Add the first numbers. In other words, do u1 plus v1 to give the first component of u plus v, and then add the second numbers together to get u2 plus v2, and then add the third numbers together to get u3 plus v3. And if we can multiply the vector u by a number, all we do is we multiply each component by the number. Ku is the vector ku1, ku2, ku3. All I'm doing is I'm taking the component form of u, and then each one of these numbers, u1, u2, u3, I'm multiplying by k. But what is the norm of ku in terms of the norm of u? Let's calculate this. The norm of ku is the square root of ku1 all squared plus ku2 all squared plus ku3 all squared. Let's play with this. Factoring out the k squared, we can write this as the square root of k squared multiplied by the square root of u1 squared plus u2 squared plus u3 squared. But we know what the square root of u1 squared plus u2 squared plus u3 squared is. That's just the norm of u. And the square root of k squared because the square root of a number is always a positive number, must be the absolute value of k. So the norm of ku is the same as the absolute value of k multiplied by the norm of u. Now, before I go on, just emphasize this. If we have a vector, we use 2 vertical lines. When we have a number, we use 1 vertical line. The vector minus u, or -1 multiplied by u, has the same length as u, but points in the opposite direction from u. Let u and v be these 2 vectors. Find 2u plus 3v. Find u minus v, and find the norm of half u. First one, 2u plus 3v. That's 2 multiplied by -131. We can take the 2 inside the vector, multiply each number by 2 to get -262. Plus 3 times 470. Take the number 3 inside the vector. 3 times 4 is 12, 3 times 7 is 21, and 3 times 0 is 0. And then add these together. Add the first numbers together, -2 plus 12 gives me 10. I add the second numbers together, 6 plus 21 gives me 27. And I add the third numbers together. 2 plus 0 gives me 2. Find u minus v, same idea. Just look at the first numbers first of all, -1 minus 4, it's -5. And then look at the middle numbers, 3 minus 7. And then look at the third numbers, 1 minus 0. And then thirdly, we're asked to calculate the norm of a half u. I'm going to use the previous calculation that we did because the norm of a half u is equal to the absolute value of a half multiplied by the norm of u. But a half is a positive number, so the absolute value of a half is just a half. So that's a half multiplied by the norm of u. For the norm of u, we use our formula, square root of u1 squared plus u2 squared plus u3 squared. I will leave it for you to check that this is a half multiplied by the square root of 11. Very quickly, I want to run through some properties of the vector operations. On this slide, u, v, and w in bold are vectors. A and b, which are not in bold, are numbers. Rule number 1, if we're adding 2 vectors together, it doesn't matter which order we do them in. U plus v is the same as v plus u. Adding 3 vectors together, again, doesn't matter the order. Bracket u plus v bracket plus w is the same as u plus bracket v plus w bracket. U plus the 0 vector is always the vector u. U plus minus u is always the 0 vector. 0 multiplied by u is always the 0 vector. Now, let me pause here just to take note. The 0 on the right is the 0 vector. The 0 on the left, just here, this is not the 0 vector, this is the number 0. Moving on, rule number 6. 1u is equal to u. The number 1 multiplied by u is always u. If we have 2 numbers and 1 vector, which we want to multiply together, order doesn't matter. A multiplied by bu is the same as ab multiplied by u. A multiplied by u plus v is the same as au plus auv. And finally, a plus b multiplied by u is the same as au plus bu. as we would expect. Now, just be careful, we can't multiply two vectors together. We can multiply a vector by a number, but we cannot multiply two vectors together. Please never write UV in your calculations. This doesn't mean anything. We can't multiply two vectors together. Next idea, unit vectors. A vector u is called a unit vector if and only if the norm of u is equal to 1. That's what it means. It just means the length is equal to 1. So for example, I'm saying that the vector 2 to the power minus a half, comma a half, comma minus a half is a unit vector. And to show that that is true, we calculate the norm of u. We put the numbers in. Now I'll leave this for you to check. And we get 1. It's equal to 1, therefore it is a unit vector. In R2, there are two standard unit vectors. They are they are the vectors 1, 0 and 0, 1. And these vectors are called I and j. In R3, we need three standard unit vectors, I, j, and k. I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. If we have any vector in R3, we can write it like this. We can write that v is v1, 0, 0 plus 0, v2, 0 plus 0, 0, v3, just by splitting these up. But then the first one is just v1 multiplied by I, the second one is v2 multiplied by j, and the third one is v3 multiplied by k. That gives us two different ways to write a vector. We could write a vector as v1, v2, v3, or we could write it as v1i plus v2j plus v3k. And we're going to use both types. We use whichever one makes sense for that particular calculation. Now, note that if the norm of v is not equal to 0, that's the same as saying that our vector v is not the 0 vector. Then I'm saying that v divided by norm of v is a unit vector. And that's true because if we calculate the norm of v divided by the norm of v and rearrange it, basically we're doing norm of v divided by norm of v, which of course is just 1. So that gives us two vectors which point in the same direction. V and v over norm of v both point in the same direction, but this orange vector, v over norm of v, is always a unit vector. Anytime we need to find a unit vector which points in the same direction as a vector v, we'll use this trick. We'll just take our vector v and we'll divide by its norm. Here's an example. Find a unit vector u which points in the same direction as P1, P2, where P1 and P2 are these points. We are going to calculate P1, P2. We're going to calculate the norm of P1, P2, and then our unit vector u will be P1, P2 divided by the norm of P1, P2. First of all, to find P1, P2, we do terminal point minus initial point, P2 minus P1. We get the vector which we could write two different ways. We could write this as 2, 2 minus 1, or we could write this as 2i plus 2j minus k. Next, we need the norm of this vector. I'll leave it for you to check that the norm of this vector is 3. And then the vector that we want, the unit vector that we want, will be P1, P2 divided by the norm of P1, P2. And I leave it for you to check that that's 2/3 I plus 2/3 j minus 1/3 k. Here's another example from a textbook. If v is the vector 3i minus 4j, and if this is a velocity vector, express v as a product of its speed times its direction of motion. So what it really wants is it wants a number multiplied by a unit vector. The number that it wants is the norm of v. I want to use two vertical lines here. The people that wrote that book used only one. The norm of this vector is 5. So it's going to be 5 multiplied by a unit vector. The unit vector pointing in the same direction as v is v divided by the norm of v, 3/5i minus 4/5j. So the answer to this example from the textbook is 5 multiplied by this unit vector. Another example from a book. A force of 6 newtons is applied in the direction of the vector v. Express the force F as a product of its magnitude and its direction. So again, this example is asking us to write the force into as a number multiplied by a unit vector. We know the number because we're told in the question that the number is 6. The unit vector is going to be v divided by the norm of v. So we calculate v divided by norm of v, and then we multiply it by 6 to get the answer. We can write this force as 6 multiplied by 2/3 I plus 2/3 j minus 1/3 k. If we wanted to find the midpoint of some line, let's suppose we have some line segment which joins P1 and P2. And let's suppose we wanted to find the exact middle point of this line. Then we could use the formula that the midpoint is x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. Go down to the bottom. The midpoint of the line segment joining P1 and P2, 3, minus 2, 0, and 7, 4, 4. Put the numbers in, and the middle of this line point, this line segment is 5, 1, 2. Our second chapter for today's lesson is about dot product. This is a way to combine two vectors together to get a number. And we're going to be doing the dot product in both R2 and in R3, in two-dimensional space and in three-dimensional space. First of all, in two-dimensional space, the dot product of u and v is given by the formula u1 v1 plus u2 v2. If we do this in three-dimensional space, we have almost the same thing. U dot v is u1 v1 plus u2 v2 plus u3 v3. We have a formula for the angle between two vectors. The angle between u and v is the inverse cosine of u dot v divided by the norm of u, norm of v. We could rearrange this formula to write this as u dot v is norm of v cos theta. I'll talk more about that later. Let's do some examples. The dot product of 1, minus 2, minus 1, and minus 6, 2, minus 3. What we do is we take the first two numbers and we multiply them together. 1 multiplied by -6. And then we take the middle numbers and we multiply them together. -2 multiplied by 2. And then finally we take the third numbers. -1 multiplied by -3. That gives us -6, -4, and 3. Add these together, we get our answer -7. Another example, a half I plus 3j plus k dot 4i minus j plus 2k. Again, multiply the first numbers together, a half multiplied by 4. Multiply the middle numbers together, 3 multiplied by -1. And then multiply the third numbers together, that's 1 multiplied by 2. And then add these three numbers together and we get the answer 1. Now let's use this formula which I mentioned earlier. The angle between two vectors is the inverse cosine of u dot v divided by norm of u norm of v, which I've written at the top of the screen. Find the angle between these two vectors. Looking at the formula at the top, we can see we need to calculate u dot v, we need to calculate the norm of u, and we need to calculate the norm of v. I'll leave it for you to check that u dot v is -4. I'll leave it for you to check that the norm of u is 3 and the norm of v is 7. So we're going to put -4, 3, and 7 into our formula. The angle between these two vectors is going to be inverse cosine of -4 divided by 21. And if we have a calculator, we can calculate that that's approximately 98.5 degrees or 1.76 radians. But you won't have a calculator in the exams. If you're given an exam question like this, then you don't do the last part. You just finish your answer as inverse cosine of -4 over 21. Anybody in Turkey who has a calculator could do the final step. The final step is not impressive. What would be impressive is if you could correctly calculate inverse cosine of -4 over 21. And it's entirely possible that if you were given an exam question like this, you wouldn't be asked for theta. You might be asked just to find cosine of theta. And then your answer would be that the cosine of theta, take that across, cosine of theta is -4 over 21. We might write a question in that way. Let's do another angle example. If A, B, and C are the corners of this triangle, find the angle theta. That's the angle ACB. This notation means it's the angle at the middle letter. So it's the angle at C, and it's the angle between the vectors CA and CB. So we need to calculate CA and CB. We need to calculate the dot product of those two vectors. We need to calculate the norms of those two vectors, and then we need to use the formula. I'll leave it for you to check that this is correct. I think the dot product of these two vectors is 4. The norm of CA is √29, and the norm of CB is √13. We'll put these into our formula, and we find that the angle between these two vectors, that's the angle inside the triangle, must be inverse cosine of 4 divided by square root of 29, square root of 13. And if we have a calculator, it's then easy to calculate these numbers. If we don't have a calculator, then we just finish. We can say that two vectors are orthogonal if and only if their dot product is the number 0. Now, let me remind you that we saw earlier that u dot v is the same as the norm of v cos theta. So what does orthogonal mean? Orthogonal means that either the norm of u is 0, that's the same as saying u is the 0 vector, or we can make this equal to 0 by having the norm of v equal to 0. In other words, having v be the normal vector, or we can make this 0 if cos theta is equal to 0. How can we make cos theta be 0? By choosing the angle 90 degrees. That means that if we have two non-zero vectors, orthogonal means that the angle between them must be 90 degrees. I'm saying that the vectors 3, -2 and 4, 6 are orthogonal. To prove this, we calculate their dot product. The dot product of u and v is equal to 0. Because neither one of these vectors is the 0 vector, we know that the angle between these two vectors must be 90 degrees. And these two vectors are orthogonal. We calculate their dot product, we get 0. Again, neither vector is the 0 vector, so the angle between these two vectors must be 90 degrees. The 0 vector is orthogonal to every vector because 0 dot u is always the number 0. Quickly, I want to talk about some properties of the dot product. U dot v is always the same as v dot u. It doesn't matter which order we do them in. We have a number k. Ku dot v is the same as u dot kv or ku dot v. Doesn't matter where we put the number in. U dot v plus w is u dot v plus u dot w. U dot u is equal to the norm of u squared. I'll leave that for you to check. Go back to the previous formula and you can convince yourself. The 0 vector dot u is the number 0. Now again, there's two zeros here, so just be careful. The first 0, the bold 0, is a vector. We can only do the dot product between two vectors. And after we do the dot product, we get a number. The second 0 is the number 0. Vector projections. We're going to be doing more projections next week, but for this week, just vector projections. We can project one vector onto another vector. Let's suppose u is the vector from P to Q and v is the vector from P to S. We can project u onto v. There's two ways to think about this. We might imagine that from the top we're pushing down and we're squashing u onto v to get this blue vector. Or we can think about this a different way. We could think that there's a sun up at the top and we're looking for the shadow of u onto v. And again, we would get the blue vector. The blue vector is called the projection of u onto v. There's a triangle here which I'm going to be using later. We can see from this picture that the norm of the projection of u onto v must be the same as the norm of u multiplied by cos theta. Now, I've been drawing this picture as if the angle between u and v is less than 90 degrees, but we might also have a picture like this where the angle is more than 90 degrees. Then when we projected u onto v, again, think of it in two different ways. We could either think of a sun at the top and looking for the shadow of u, or we could imagine that we're pushing down with great force and we're squashing u onto the line passing through v. Then we would get the blue vector. And then we would have a very similar triangle. Now, because the angle is slightly different, there's a minus here. The calculation I'm going to do soon, I'm going to be using the first picture. We could use the second picture and we would just get two minus signs, and two minus signs would cancel out, so we would end up with the same answer. But for the time being, I want to think about this picture where the angle between the two vectors is less than 90 degrees. The vector projection of u onto v is the vector from P to R. And what does that mean? We can calculate a formula for this, because this vector is equal to its length, or its norm, multiplied by a unit vector which points in the same direction as v, assuming that the angle between them is less than 90 degrees. The length of the projection of u onto v is the norm of the projection of u onto v. A unit vector which points in the same direction as v is v divided by the norm of v. And from the triangle, which is shown here, we know that the norm of the projection of u onto v is the same as the norm of u cos theta. So put this in. And then write it like this. I want to write it as norm of v cos theta divided by norm of v squared multiplied by v. Why did I write it like this? Because we know what this thing on the top is. We know what norm of v cos theta is. This is just u dot v. This is an important formula, so I'm going to write this as a theorem. The vector projection of u onto v, the blue vector, is given by u dot v divided by norm of v squared multiplied by v. Okay, let's do an example using this. I'm writing now the formula that we need at the top. Find the vector projection of u onto v. We're going to take the formula at the top and we're going to put our numbers in. U dot v is the same as 6 minus 4. Norm of v squared is 1 plus 4 plus 4. And then we multiply this by v. And the answer that we get is minus 4 over 9i plus 8 over 9j plus 8 over 9k. It's just putting the numbers into our formula. Find the vector projection of f onto v. Here's an example in 2 dimensions. Again, we just put the numbers into our formula. I'm going to skip past this example very quickly. You can read in the lecture notes or you can rewatch this video. Please check that the answer is minus 1 over 10i plus 3 over 10j. Verify or check that the vector u minus the projection of u onto v is orthogonal to the projection of u onto v. Picture looks like this. This is u, v, and the projection of u onto v. And the vector u minus the projection of u onto v must then be this orange vector. We are asked to check that these two vectors are orthogonal. In other words, we are asked to check that this angle here must be 90 degrees. Before I go on, remember how we add vectors together by doing them nose to tail. Blue plus orange must be the same as green in this picture. Projection of u onto v plus u minus projection of u onto v must be the same as u. Yes, the formula worked. Now, clearly the projection of u onto v is just a number multiplied by v, and this must be parallel to v. So it's going to be good enough to show that u minus the projection of v onto v is orthogonal to v. So what we want to do is we want to show that u minus the projection of u onto v dot v is equal to 0. I want to do this calculation and I want to get equal to 0 just here. If I can get equal to 0, then it's done. So that's what we're trying to do. Let's put the formulae in. So first of all, it's u dot v minus the projection of u onto v dot v. And using the formula in the yellow box at the top, I have u dot v minus u dot v over norm of v squared, v dot v. But remember, v dot v is the same as norm of v squared. And norm of v squared will cancel with norm of v squared. We're left with u dot v minus u dot v, which is equal to 0. So we've done it. We've shown that these two vectors are orthogonal. The final chapter for today is about the cross product. For the cross product, again, we're going to be using the left hand rule. Imagine holding your hand up the same way that the hand in the picture is drawn. Rotate your hand around so that your second finger points in the same direction as u, and your first finger points in the same direction, v. Then your thumb will tell us the direction that u cross v points. Let me be more precise. Let n be a unit vector which satisfies these three properties. First, n is orthogonal to u. I need the angle between u and n to be 90 degrees. N is orthogonal to v. The angle must be between them must be 90 degrees. And the direction of n is then chosen using the left-hand rule, as shown in this picture. Once we have this vector n, we can define the cross product of u and v to be u cross v is equal to norm of u, norm of v, sine theta n. Now we've seen a formula which is similar to this already today. We've seen that u dot v is norm of u multiplied by norm of v multiplied by cos theta. That was the dot product and that was a number. Again, for the cross product, we have norm of u and norm of v. We have sine instead of cos. And we also have a unit vector n. The cross product is a vector. Let me repeat that. U dot v is a number. U cross v is a vector. Okay, now I've put the formula that I want to talk about at the top. If U and V are parallel vectors, then that means the angle between them must be either 0 degrees or 180 degrees. But sine of 0 is 0, sine of 180 is 0. So U cross V, if we have a 0 here, must be the 0 vector. U dot V equal to 0 means the vectors are orthogonal. U cross V equal to the 0 vector means either U is the 0 vector or V is the 0 vector, or these two vectors are parallel. Properties of the cross product. Again, I'm going to be very quick here. U, V, and W are vectors, R and S are numbers. RU cross SV is the same as RSU cross V, doesn't matter where we put the numbers. U cross V plus W, this is one we would expect, I think. U cross V plus U cross W, one we perhaps don't expect. V cross U is minus U cross V. I'm going to talk a little bit more about that in a moment. If we combine number 2 and number 3 together, we get V plus W cross U is V cross U plus W cross U, which is what we expect. And 0 cross U is 0. You can check that from the definition on the previous slide. And one which is perhaps not obvious, U cross V cross W means U dot W multiplied by V minus U dot V multiplied by W. Now let me just check, does this line make sense? V and W are vectors, so V cross W is a vector, and then U cross this vector is vector cross vector is vector. Okay, left side makes sense, and left side is a vector. What do we have on the right side? U dot W is a number, and then we do number multiplied by vector, which is vector. And then minus, again, number multiplied by vector. On the right side, we have vector minus vector, which is vector. So yes, that makes sense, and that's also a vector. That doesn't prove that this line is true, but it proves that at least it makes sense. Let's talk about property 3. If we're doing U cross V, we hold our left hand like this. We put our second finger on the vector U, and we point our first finger in the direction V. And then our thumb points upwards, so U cross V must point upwards. Now let's suppose instead we're looking at the picture on the right. Let's suppose we're doing V cross U. And now we need to change our hand position so that our second finger points in the direction V and our first finger points in the direction U. Where does our thumb then point? Then our thumb points downwards. In this picture, V cross U must point downwards. That's why V cross U is minus U cross V. These two vectors have the same norm, but one vector points in the opposite direction from the other vector. Today is going to be a longer than average lesson. I'm going to be another 15 or 20 minutes before I finish. We can talk about the area of a parallelogram. Let's suppose we have a parallelogram which we use the vectors U and V to draw like this. Area of a parallelogram is the length of the base multiplied by the height of the parallelogram. The base is easy, that's just the norm of u. For the height, we use trigonometry to see that the height is the norm of v multiplied by sine theta. So we get norm of u, norm of v, sine theta. But that sort of looks like what we have at the top. The only difference is at the top we have a unit vector n. But a unit vector just has norm 1. So if we take the norm of u cross v, we just get multiplied by 1. The area of this parallelogram is the norm of u cross v. Rather than parallelograms, I'm more interested in triangles. From this picture, it's straightforward to say that the area of this triangle is a half of the area of the parallelogram. So the area of this blue triangle must be a half u cross v. We'll come back later and use this formula. First, I want to find a formula for u cross v. Let me remind you of the three standard unit vectors, I, j, and k. What do we get if we do I cross I? Well, that's norm of I, norm of I. The angle between I and I is, of course, 0, so sine 0, multiplied by some unit vector n. But sine of 0 is just equal to 0. So we just get the 0 vector. For the same reason, j cross j is 0 and k cross k is 0. But what about the other possibilities? What about I cross j, for example? Hold your left hand up in front of your screen and turn your hand so that your second finger points in the direction I and your first finger points in the direction j. Where does your thumb point? Your thumb then points in the same direction as k. So I cross j must point in the same direction as k. So I cross j must be norm of I, norm of j, sine 90 degrees, because the angle between I and j is 90 degrees, and then the unit vector we're using is k. What's the norm of I? That's just 1. What's the norm of j? That's just 1. What is sine of 90 degrees? It's just 1. So we end up with just k. And then immediately we have that j cross I is minus I cross j, or minus k. The other 4 I'm going to leave for you to check. Pause the video if you rewatch this video, or when you're looking at the lecture notes. Hold your left hand in front of the screen or in front of the paper and turn your hand around and convince yourself that j cross k is I, k cross j is minus I cross k is minus j, and k cross I is j. I'm going to move forward quickly. Please do check that later. Now, let's suppose we have just any two vectors, u and v. I want to calculate a formula for u cross v. So I'm going to be doing u1i plus u2j plus u3k cross v1i plus v2j plus v3k. We're going to be multiplying these together. We do first term cross first term, and then first term cross second term, first term cross third term, second term cross first term, second term cross second term, and so on. 3 multiplied by 3 is 9. We're going to end up with 9 terms. Here they all are. For example, first term cross first term is the same as U1 V1 I cross I. And first term cross second term is the same as U1 V2 I cross J. And so on. Now, we can simplify this. Remember that I cross I is 0. So we can forget about this, that's just 0. J cross J is 0. So there's another term we can forget about, that's just 0. And K cross K is just 0, so forget about this. Then we're left with 6 terms. And we know what to do here. I cross J, we know is the same as K. I cross K, we know is the same as minus J, and so on. I get 0 plus U1 V2 K minus U1 V3 J, etc. Rearrange this to group the I terms together, the J terms, and the K terms together. And we get the formula that we want. This is an important formula, so I'm going to write this as a theorem. U cross V is U2 V3 minus U3 V2 I minus U1 V3 minus U3 V2 J plus U1 V2 minus U2 V1 K. I'll put this at the top of the slide soon when we start using this. Now, some of you would have studied matrices and determinants at high school. So if you already know what matrices and determinants are, then you might want to use this formula instead. If you don't know what matrices and determinants are, then it doesn't matter. You use the formula that I gave on the previous slide. Find U cross V and V cross U if U and V are these vectors. I'm going to be using the formula at the top of the screen. First, I want U2 V3. U2 is 1 and V3 is 1. So that's 1 multiplied by 1. And then it's minus U3 V2. U3 is 1, V2 is 3, so it's 1 multiplied by 3. We get 1 minus 3. And then it's U1 V3. U1 is 2 and V3 is 1, so 2 multiplied by 1. U3 V1, 1 multiplied by minus 4 to give minus 4, and so on. U1 V2, 2 multiplied by 3, and then finally it's U2 V1. One multiplied by minus 4 to give minus 4. We end up with minus 2i minus 6j plus 10k. And then straight away we can use a shortcut. V cross u is the same as minus u cross v. So that's just 2i plus 6j minus 10k. Find a vector perpendicular to the plane containing the points P, Q, and R. Now, we can find two vectors in this plane easily. We can find PQ and we can find PR. How could we find a vector which is orthogonal to these two pink vectors? We do what we always do, we just take their cross product. we're going to be calculating PQ cross PR because PQ cross PR is orthogonal to PQ, angle is 90 degrees, and PQ cross PR must always be orthogonal to PR. The angle between them is 90 degrees. So we calculate PQ and PR. I'll leave these for you to check. I'm being deliberately quick here. And then we calculate PQ cross PR. Again, I'm going to be very quick. At a later time, please check that this is 6i plus 6k. Find the area of the triangle PQR. It's the same PQ and R that I used in the previous example. We have a formula for the area of a triangle. The area is a half multiplied by the norm of PU cross PR. We already calculated this product, this cross product. We already know it's 6i plus 6k. So this is a half multiplied by the norm of 6i, 6k. And again, I leave that for you to check, is 3 square root of 2. And this is the way that you should be leaving your answer if you're given an exam question like this. I don't want you to calculate the exact decimal number. I just want you to give it in this form, something like 3 root 2. Find a unit vector which is perpendicular to the plane containing P, Q, and R. Again, same points P, Q, and R as in the previous two examples. We've already found a vector which is perpendicular to this plane. We just need to find a unit vector which points in the same direction. So we just need to normalize this vector. Remember how we did this earlier? We just take our vector and then we divide by its norm. So it's going to be 6i plus 6k divided by the norm of 6i plus 6k. Another area of a triangle question. A triangle is inscribed inside a cube of side 2 as shown below. Use the cross product to find the area of this triangle. Now, before I go on, let me just point out, if a question says that you need to do a particular method, then you have to use this method. If you correctly calculated the area of a triangle but you used a different method, then you would get 0 points. If a question says that you have to use the cross product, then you have to use the cross product. So how do we do this? The first thing we need to do is we need to draw some coordinate axes. And we could draw these wherever we wanted. We could put the origin anywhere we wanted. I'm choosing to put the origin, to put the point 0, 0, 0 on the back corner of the cube. But that doesn't matter. You could put the origin wherever you wanted. If we do it this way, if we put the origin at the back corner, then we can find coordinates for the 3 corners of the triangle. The corner at A must be at the point 2, 0, 0. The corner at B must be at the point 2, 2, 0. And the corner at C must be at the point 0, 0, 2. And then we can use our previous method. We can choose 2 vectors. I can tell you I'm going to use the vector from A to B, and I'm going to use the vector from A to C. I'm going to do the cross product of these 2 vectors, calculate the norm of their cross product, and then divide by 2. So AB must be the vector 2j, and AC must be the vector minus 2i plus 2k. I leave that for you to check. I'm going to skip on quickly. I'm also going to leave it for you to check that if we do the cross product of these two vectors, we get 4i plus 4k. And then we use our formula. The area of the triangle is a half multiplied by the norm of AB cross AC. And I leave it for you to check that this is 2 square root of 2. One more definition. The triple scalar product of u, v, and w in this order. First u, then v, then w is u cross v dot w. Does that make sense? U and v are vectors, so we can do u cross v and we get a vector. And then it's vector dot vector. That gives us a number. Hence the name scalar product. This is a number. What could we use that for? We could use that to calculate the volume of a three-dimensional shape like this, which is called a parallelepiped. The volume of this object is the area of the base. We already know the area of the base because that's just the area of a parallelogram multiplied by the height. For the height, we can use trigonometry. That must be the same as norm of W cos theta, where theta is the angle between W and U cross V. And then when we multiply these together, we see this is the same as the absolute value of the triple scalar product of U, V, and W. I'm not going to do any examples using that. I'll just leave that for you to. I'll just leave that there for you in case you need it. One final comment. We could do the dot product in both R2 and in R3, both two-dimensional space and in three-dimensional space. But we can only do the cross product in three-dimensional space. Why is that true? Remember, when we're defining the cross products, we have to use our left hand to decide the direction. We can't use our hand in two-dimensional space. We can only use our hand in three-dimensional space. So just be aware that there is no cross product in two-dimensional space. And that brings us to the end of today's lesson. Next week, we're going to be talking about lines, planes, and projections. Are there any questions? The exam will be face-to-face. I made an announcement about this. Let me check it out. It's currently scheduled for Tuesday, the 23rd of November at 1 o'clock. If you look in O-Learn at the announcement section, you'll see I made a note there. If the exam changes, then I'll update that. It will be a face-to-face exam on campus. It will be everything that we cover before the exam. So let me check the syllabus. It will include chapter 19. It's undecided, but you will have to show how you solve them. If you look in the course content section, you'll see I've posted the last exams that we gave face to face before the pandemic. I'm guessing that somehow the format will be somehow similar to those. Be something like that.